In all of the harmonic motion and circular motion that we've looked at so far, the object in question has always started at the middle of a cycle, at the top, or at the bottom. And that's the nicest case because then you can just use an unshifted sine or cosine to describe the harmonic motion. But that doesn't always happen. So let's look at an example where it's not so nice. So here we have an object moving around a circle at 3 rotations per minute, and this circle has a radius of 25 units, could be feet, I guess. And let's say that this initial angle that the point starts at is minus pi over 6 radians. And let's find the height of this point moving around the circle as a function of time. So because it's a height, we know we're going to use sine, but we need to know the angle that's going to go into that sine function. So first let's concentrate on finding the angle that this point has rotated through as a function of time. Okay, well, its initial angle is minus pi over 6, and the angle that it's rotated through is increasing 3 rotations per minute. Of course, 3 rotations per minute, we should convert that to radians per minute by multiplying by 2 pi. So that's 6 pi radians per minute. So the angle theta as a function of time is 6 pi, that's the angular speed, times time, minus the initial angle. And now we can use our usual tricks for harmonic motion and circular motion to write down the y-coordinate as a function of time. So it's the radius, 25, times sine, since we're talking about a y-coordinate, sine of 6 pi t minus pi over 6. Okay, there we go. And you notice that having this initial angle of minus pi over 6, it caused there to be an angle here in our sine function. This angle is called a name. It's called has a name. It's called the phase angle. Okay, and so this phase angle is pi over 6. Sort of by convention, that minus sign isn't part of the phase angle. So this phase angle is pi over 6. Now, it's important to realize that this phase angle, it's genuinely an angle. So this is in radians. Okay. It looks kind of like a horizontal shift, but a horizontal shift in this graph would be a shift in time. And this shift is an angle shift. It's not a time shift. So this isn't a horizontal shift in the graph. You can find the horizontal shift if you want to. And the trick to do that is, inside your sine function, just factor out the angular speed here. So if we factor out 6 pi inside of our sine function, then we have 6 pi times t minus, and so the pi factors out, so you're left with a 1 in the numerator, and we need an extra copy of 6 in the denominator, so 6 times 6 is 36. Okay, just to check that, you can distribute this 6 pi back through to make sure that you get what we had before. So now this quantity here, this 1 over 36, this is genuinely a shift in time. You can tell it must be the units must be in time because it's being subtracted from t, and t is in time, has units in time. So the horizontal shift for this situation is a shift right by 1 over 36. So you can see that the phase angle and the horizontal shift are related, but they are not the same thing. So you have to be a little bit careful about that. In general, if you have a sinusoidal function that looks like, say, an amplitude times sine of kt minus c plus some mean value b, so the phase angle here is just c. And then if you play this algebraic trick to find the horizontal shift by factoring out the angular speed k, you get sine of k times t minus c over k. And so we find that the horizontal shift, it's a shift rightward, and it's not c, it's c over k. So have to be a little bit careful about this distinction between phase angle and horizontal shift. So let's look at a couple examples. All right, first example, let's find the phase angle for this sinusoidal function, sine of pi over 2 times t minus 1. So remember this one in here, because we already have our k value factored out, this minus 1 here, that is the horizontal shift. It is not the phase angle. The phase angle is what you get when you distribute this value of k. So let's distribute k. So f of t is sine of pi over 2t minus pi over 2. All right, so now this right here, this is our phase angle. So for this example, our phase angle is pi over 2. And again, that minus sign isn't part of the phase angle, just by convention. All right, let's look at another example. Let's find the phase angle for this function, sine of pi over 2 times t plus 2. We'll play the same game, just factor out that pi over 2. So this function becomes, distribute that pi over 2. This function becomes sine of pi over 2t plus pi over 2 times 2 is just pi. Okay, so it's tempting to say that the phase angle is pi, but remember, to have the phase angle, we need a minus sign in the middle right here, and we have a plus. So the phase angle isn't pi. To see what the phase angle is, we have to arrange for there to be a minus sign here. And we can do that by having two minus signs like this. So now we see that the phase angle is minus pi. Okay. Of course, so this is going from a function that's a sinusoidal function that has the horizontal shift apparent to making it so that the phase angle is apparent. You can go the other way. So here's a sinusoidal function where the phase angle is obvious. So right here, this is the phase angle, 2 pi over 3. And let's find the horizontal shift for this function. Well, as before, we can just factor out our angular speed, which is 2 pi. So sine of 2 pi times t minus a third. And so the horizontal shift here is a third, and it's to the right. Okay. Now, one reason why the phase angle is important is because in many physical situations, you want to compare two sinusoidal functions, and how their phases compare usually has a big impact on how the physical situation works out. So it's important to know what the difference in phase between two sinusoidal functions is. So if you have two sinusoidal functions, so I'm going to call them y1 and y2. So the first one will have some amplitude times sine of, for this all to make sense, the two sinusoidal functions will need to have the same angular speed, so the same period as well. So kt minus, so let's call our first sine shift, or our first phase shift c1. And for our second sinusoidal function, let's call the amplitude a2 times sine of, and again, the angular speed needs to be the same for these two, so k times t minus, and then our second phase angle, we'll call that c2. So to compare the phase of these two, what we'll do is we'll just subtract these two phases. Okay, so this is called the phase difference. Here we go. So the reason the phase difference is important is because it turns out that if the peaks and troughs of two sine curves exactly line up, then that turns out to be physically interesting. And if they don't line up, then that sort of affects the physical situation in a different way. And the phase difference will let us tell when the peaks and troughs of two sine curves are when they coincide. So to see how that works, let's just sketch two sine graphs that have the same angular speed. So here's one. The amplitudes don't have to be the same. So I'm going to draw this one with a smaller amplitude, but the same period. Okay, and you can see here the peaks and troughs are the same. Okay. So let me put that horizontal axis here. Okay, so a change in phase moves the peaks and troughs, rightwards and leftwards, since phase difference corresponds to a horizontal shift, or is related to a horizontal shift. So how could it be that these two functions have their peaks and troughs in the same place? Well, one way would be if these shifts were exactly the same. So one way to have these things match up is if C1 were just equal to C2. But another way to have the peaks and troughs match up is, right, sine is periodic. So if we shift what's inside this sine function by a period, which is 2 pi, then by a period, an angular period, which is 2 pi, then these again will coincide. That would correspond to sliding the peak of one of these, of the red graph, all the way over to here. Then this first peak would match up with the second peak in the blue graph. But since the red graph is periodic, still all the peaks and troughs would match up. So it's not necessary that C1 and C2 be exactly the same to have the peaks line up. We could have C1 plus any multiple of 2 pi to be equal to C2. So another way to say that is that C1 minus C2, or the phase difference, is some multiple of 2 pi. Okay, and so this this tells us that for peaks and troughs to line up, we want the phase difference to be a multiple of 2 pi. So if the phase difference is a multiple of 2 pi, that's when the peaks and troughs line up. That is called in phase. Otherwise, if the phase difference isn't a multiple of 2 pi, then we say that these two sinusoidal functions are out of phase. Okay, so let's look at an example. Here are two sinusoidal functions. Are they in phase or are they out of phase? So we need to tell if they're in phase or out of phase. We need to calculate the phase difference. So we need to know the phase angles for both of these sinusoidal functions. Of course, the way that they're set up, these shifts that we can see here, these aren't phase angles, these are time shifts. So first we need to find the phase angle for these two. I should label this one y1 and this one y2. So first, let's work on y1. So we need to find the phase angle for this, and to find a phase angle, we can just distribute this angular speed. We get sine of pi over 3t plus pi over 4. Okay, so this first phase angle, we could call it C1, is negative pi over 4. Remember, a positive in the middle here corresponds to a negative phase angle. And for y2, we can do the same thing, distribute the angular speed. We get 2 times sine of pi over 3 minus, let's see, 21 over 3 is 7, so 7 pi over 4. So the phase angle for y2, we could call that C2, is 7 pi over 4. Okay, now that we know the two phase angles, we can find the phase difference, which is just C1 minus C2. So negative pi over 4 minus C2 is 7 pi over 4. That's minus 8 pi over 4. That's minus 2 pi. So we see that the phase difference here is a multiple of 2 pi. So y1 and y2 are in phase. If we graphed y1 and y2, their peaks and their troughs would coincide.